Now that we have considered how to do a single-step synthesis problem involving Grignard reagents, we are now ready to attack the more difficult problem of a multi-step synthesis. So what I'm going to do in this lesson is bring you back to the molecule that I first introduced you to in lesson 1 and said we will learn how to do this in the course of this unit, and go over now how you would solve such a problem. There is still one missing link that I won't be able to cover in complete detail until we finish the last topic for this unit, but we are now in a position where we can get the overall strategy and the overall structure of what a solution will look like. So just to remind you, the problem that we're trying to solve is to prepare the 14-carbon tertiary alcohol indicated on the screen from starting materials that contain 6 carbons or less. So your tertiary alcohol has a cyclopentyl group on it, a phenyl group on it, and an ethyl group on it. So given that it is a tertiary alcohol, we should dig into our toolbox and think, okay, this will be made from a Grignard reagent plus a ketone. So in order to have molecules that are the proper size, there are 2 reasonable disconnections. Once again, one of them is indicated in blue and the other is indicated in purple. So the purple disconnection would be to react phenyl magnesium bromide, a 6-carbon Grignard reagent, with cyclopentyl ethyl ketone, an 8-carbon ketone. The blue disconnection reacts cyclopentyl magnesium bromide, a 5-carbon Grignard reagent, with phenyl ethyl ketone, a 9-carbon ketone. Okay, further analysis. So regardless of which disconnection we choose, the Grignard reagent fits the constraint of the problem in that it is 6 carbons or less. However, the ketone does not fit the constraint of the problem. The ketone is either, depending on which disconnection we choose, an 8-carbon ketone or a 9-carbon ketone. So the ketone is going to be need to be made from 2 smaller pieces. That's why this becomes a multi-step synthesis problem rather than a single-step synthesis problem. So if we go with the purple disconnection, the problem reduces to the following. Prepare cyclopentyl ethyl ketone, 8 carbons from starting materials of 6 carbons or less. Now, how do we make a ketone? In all of the effective carbon-carbon bond forming reactions involving Grignard reagents that we have learned to date, the product is an alcohol, not a ketone. Now, if there were a reaction that could do the following transformation, that can take the secondary alcohol on the left and turn it into the ketone on the right, would that help us solve this problem? And the answer is yes, absolutely. Because we would be able to make the required alcohol, still 8 carbons, in a single step through a Grignard addition to an aldehyde. Okay, so the 8-carbon alcohol can be made from cyclopentyl magnesium bromide, which is 5 carbons, plus propionaldehyde, which is 3 carbons. Or it can be made from the 6-carbon aldehyde plus a 2-carbon ethyl magnesium bromide, depending on which bond ending at the carbon containing the OH you choose to use for your disconnection. So what's the missing link? Well, reactions that convert secondary alcohols into ketones are called oxidations. And we will learn about oxidations in the next several lessons. But before we go there, what we can do is put this all together, and I can give you, as I said, the outline of one possible solution. So the first reaction you would carry out would be a Grignard reaction. And just for the sake of argument, I'm going to start with cyclopentyl magnesium bromide plus propionaldehyde. So you write down your two starting materials, say that first you're going to mix them together in ether, and then you're going to do an aqueous workup. So that's the 1 and 2 above and below the arrow, and that's going to give me the secondary alcohol product. Our second reaction will be an oxidation, in which we take the secondary alcohol and convert it to the ketone. The only thing that I cannot do yet is write the exact reagents above the arrow that accomplish this transformation, because we have not yet learned the right reagents. We will learn that in a couple of lessons. And then finally, you do your second Grignard reaction, where you take phenylmagnesium bromide, react it with the 8-carbon ketone. Again, mix them together in ether as a solvent first. Then you do an aqueous workup, and that gives the tertiary alcohol 14-carbon product. Okay, so the structure that I want you to get out is, for these tertiary alcohols, you can make them using a Grignard oxidation and a second Grignard sequence. It is a 3-step synthesis. Now, I just want to note in closing that we use the word step to describe mechanisms and syntheses, but they are very different beasts. Each reaction in your synthesis, each step in your synthesis, so to speak, has its own mechanism that has a number of steps itself. The issue with a synthesis is that you put together the reagents and that reaction happens on a particular day. You can stop after step 1, or what I call reaction 1 here, go home, come back the next day, do reaction 2, go home, come back the next day, and do reaction 3. So the end of each step of a synthesis, each reaction of a synthesis, is a logical stopping point. Whereas a mechanism you have no control over, because once you mix the reagents, they are going to go through all of the steps of that mechanism in the pot until you get to the end. Okay, so I hope I made clear the distinction between steps in a mechanism and steps in a synthesis. So all we have left to do is fill in this detail about the oxidation reaction. But before we go over exactly which reagent you need for an oxidation, I'm going to back up a little bit and discuss oxidation and reduction reactions in general in the context of organic chemistry, and how you assign oxidation states and recognize such reactions. So that will be the subject of the next lesson.